Acoustic measuring devices are used to record the time it takes for an impact-induced stress wave to travel through the wood sample. A stress wave is created with a strike to the tree through an accelerometer that emits a start signal to a timer. A second accelerometer, attached to the opposite side of the tree, senses the leading edge of the stress wave, sending a stop signal to the timer. Time of flight, measured in microseconds, is combined with the measurement of distance between sensors to calculate a transmission time per unit length, such as microseconds per meter, or velocity, such as meters per second. Stress wave propagation in wood is related to the physical properties of the wood. Stress waves travel faster in defect-free wood. Areas of cracks, cavities, or decay-induced low density will require longer times for the stress wave to arrive at the opposite timing sensor. With multiple measurements from an array of timing sensors, computer software can create a projection or two-dimensional map of the acoustic characteristics of the sampled area. Acoustic tomography employs multiple sensors, usually 8 to 32, to measure stress wave transmission times at multiple directions. The distance between the sensors is measured with a caliper scale. An impact-induced stress wave is generated by striking each of the sensor recording points with the hammer. A computer records the stress wave's time of flight to each of the other recording points. Knowing the distance and the time of flight, velocity can be calculated by the computer. Computer projection software using stress wave data from multi-path measurements creates an image of the distribution of relative sound wave velocity in the cross-section. The tomogram in this example is displayed in 4 colors representing varying recorded velocities. Velocities are displayed from low to high as blue, violet, green, and brown. This map of the acoustic characteristics of the sample cross-section with accurate interpretation can determine the size and location of internal trunk decay and defect. Proper interpretation is critical. The tomogram is not a spatially precise map of the internal structure. It is only a representation of the wood's acoustic characteristics as determined by the perceived velocities of stress waves moving between the sensors. Comparisons between the tomogram and the actual tested cross-section illustrate how the tomogram shapes will vary depending upon the type of decay and defect within the trees. Acoustic displays of cracks, for example, are usually overstated in the tomogram. Areas of low velocity could be a result of decay, hollow, snake crack, or ring crack.